Okay. What have you learned last week, Lu Jiaming? Are you here, Lu Jiaming? What have you learned last week? Any idea? Miss or Mr.? Okay. What about you on mailing? What can you remember the content last week? On mailing, are you here on mailing? What have you learned last week? Yep, we learned about the diffusion. Then what else? What else we have learned? Chu Zhang Heng. What have we learned last week? Chu Zhang Heng, are you here? Should be last week lah, because last week is a test. What have we learned last lecture? Okay, just not on mailing. Tell us about diffusion. What is another one? Chu Zhang Heng. Okay, sorry for the disconnection just now. Okay, Chu Zhang Heng, what have we done last week? Can you hear me, everyone, right now? Yes, Chu Zhang Heng, where are you? Okay. Wong Ka Sing, what about you? Hall effect? Okay. What is the Hall effect about? Why do we need Hall effect? Wong Ka Sing, can you elaborate more? Why do we need Hall effect or Hall device? What is the purpose of the Hall device? Yep, to find the mobility. Another one? Kupun Keong, what do you think? Instead of looking for the mobility, what is next? Kupun Keong, are you here, Kupun Keong? What have we learned last week? Last lecture? Instead of using the Hall device to find the mobility, what else can we find from there? Can you still remember or you already forgot? Yeah, Mr. Cool, where are you? Why is every one of you already forgot everything? Okay, Hu Heng Dong, what about you? What can you remember? Hu Heng Dong, are you here? I'm asking Hu Heng Dong right now. Hu Heng Dong, are you here? Hu Heng Dong? Yes, we are looking for concentration. But what concentration? We are using whole device to find the concentration. What kind of the concentration? Is either whole concentration or the what? The electron concentration only. One important word. I know it's a carrier concentration. But what is the important word? Start with M. Hu Heng Dong? You can get some hint from the one answer by Lu Jianming. So any idea? Start with M. Mobility already mentioned just now. Yep, majority. Okay, we're using the Hall effect to find these two items. Okay, very simple, but very simple thing. Actually, when you look back to a slide, you also can find the answer. Okay, just now, some of you mentioned about the diffusion. Besides diffusion, what are the next one? We got two types of the transportation. One is the diffusion. What is another one? 悄悄修. Are you here? 悄悄修. Yep, drift. So we have a diffusion current density and the drift current density. So basically, this is all the content that we have learned for the last lecture. I'm not sure whether how hard is it. Some of you can forget everything like this. You guys better keep improving yourself because in every lecture, I will pick some of you to answer my question. Okay? So please remember this. For those who cannot answer my question and just keep quiet, I will kick you out from the classroom. Okay, so let's talk about the thing today. So last time we learned about the N type and the P type. So when we're talking about the N type, we know that the electron is the majority. And then P type, the majority is the hole. Okay? So what if we combining these two things together? So for example, if we are combining P-type semiconductor in here, and then N-type semiconductor is here, and then if we connect it to the circuit, okay, we know that N-type is full with the electron, while the P-type is full with the hole. Okay, so imagine originally, okay, your P-type, let's say P-type is here, N-type is here. Originally, P-type is full with all the positive charge or hole. Okay, the N-type is full with all the electron. Originally, but when you are combining these two things together, so they start to have some kind of the reaction. Imagine this one is in the open circuit. You didn't connect anything. This is open circuit. But since you have a p-type and an n-type here, you can see that here the majority is the high concentration of the hole, high concentration of the electron. And some of the electron may have attracted to here. In the other word, some of the electron will move to here. Not all, but just part of it. Since some of the electron already moved to here, they will be lefting some hole over here, or here. Then you can see that all the electrons starting to gather in this area. But the gather place for them is on the junction there only. So when you are having this, let's say if you remove this part, you are going to have one region, this region and this region. Negative over here, positive over here. Okay, this region we call it as a space charge depletion region. Then you got some kind of the distance, which is W, and also the voltage. Okay. So at this point, can you understand? Clear this part? If you think okay, then that okay. VBI I will explain later. Okay. At first, understand the theory here first. Okay, the remaining of you, can you understand? Okay, so let's proceed. So, imagine that if we have something like this. Originally, if you didn't connect anything, it will become like this. We call this thing as a zero bias. If the circuit is open circuit, which means that everything is in the thermal equilibrium. If we didn't connect anything, this thing is open circuit, we call it as a thermal equilibrium. But imagine, let's say, if we are connecting this thing into this way, positive over here, negative over here. Okay, if we connect this way, we'll see what happens. Imagine if we are connecting the positive side, p-type side into the positive, n-type side connect to the negative. Those positive charge here, it will coming to this way, coming to this way, coming to this way. Those negative charge will be going to here, here, and here. Which means that right now, this thing, the concentration of the hole will be increased. And then this region will be getting smaller and smaller because you are getting more and more positive charge here. Same thing happened to the other side. If we are going to have an n-type, then this region will be getting smaller, smaller, smaller. All negative charge will be coming here. So just now I mentioned that here is the W. So in this connection, we call it as a forward bias. So in the zero bias, W, nothing changed. But if in the forward bias, the W will decrease. Okay, because it's providing the additional positive charge and negative charge to make the W smaller. So you can see that the W will be decreased. At this part, can you understand the forward bias? Forward bias means that positive will connect to the positive, negative connect to the negative. Okay, at this point, theory part, can you understand? Okay. The remaining of you? Okay. All right. So thank you for the response. So imagine if we have the other circuit. So draw it. There's a line. So originally this one is a P and N. So here's a negative, positive, N. But right now imagine if we reverse the battery. So right now, negative is in here, positive is here. So what will happen? If we are having this connection, we will call this one as the reverse bias, VRC. Okay, because it's connect reversely. But what will happen in the W side? Imagine you have all the positive charge here. You can imagine that all the positive are attracted to here. Or maybe your electron coming to here. And then he will start filling up the part. And hence, make the width become wider. Same thing happen here. Positive charge to here, increase the positive charge, and the width will become increased. So in the other word, if in the reverse bias, the width will increase. Okay, at this point, can you understand? Okay, very simple. So let's see back to the slide. Okay, this thing we call it as a PN junction because we are going to connect the P and N together. So most of the semiconductor device will be having at least one junction between P and N. So one region is doped with the acceptor impurity, which is a P region. Another one doped with the donor atom, which is the negative one. That interface we call it as a metallurgical junction. So let's see the graph. So we will consider a step function in which the doping concentration is uniform in each region, which means that if we are looking at this slide, use my pen. Okay, so this is a P, and this is an N, P and N. So the concentration throughout the P junction will be the same. Concentration throughout the N junction will be also the same. And then somehow, in between her, there will be a very large density gradient. Okay, large, huge changes. Okay, so as I mentioned just now, this will form a region here. This will form a region here. So this thing we call it as a space charge region, or we call it as a space charge depletion region. Both are the same thing. Okay, so this is the picture that I mentioned just now. An A negative charge, positive charge, space charge region. You'll be having an electric field. Then the force onto the hole coming to here, force onto the electron to here, to here. Then you can see that the diffusion force is coming from the high concentration to the low concentration. So that's why you can see that the whole diffusion will go into in this direction. The electron concentration diffusion force is coming from this direction. Okay. Just now I mentioned that if we didn't connect anything, open circuit, we call it as a zero bias, which is this diagram. Okay, zero bias. And then we can also see that here is the changes of the energy level from P to N. Okay, so the properties of the step junction in the thermal equilibrium, if there's no additional energy provided. In the other word, you didn't provide any battery or electrical energy there. So we can determine the space charge width, which is the W, electric field, and also the potential through the diffusion region. This answers the question just now. VBI stands for the voltage, okay, in between the small region there. Okay, if we assume that there is no voltage is applied across the PN junction, then the junction is in the thermal equilibrium, which means that if you didn't provide the battery over there, it will be the thermal equilibrium. But the interesting thing is this thing. So when you can see that from P junction to N junction, you can see that the energy level for the EC, last time we learned about the EC, okay, conduction band energy, it will drop in this way. And then the Fermi intrinsic energy level, it will also dropping. Then the Fermi for the energy, valence band energy, it will also dropping. Fermi energy level, okay. Remember, we have the difference between the EF1 and EF. So you can see the gap here, okay? This is the gap for the FP, the gap for the FN. Later, we will come across more on this thing. But let's see this thing first. Okay. Electron in the conduction band of the N region will face the potential barrier, which means that in this region, okay, electron from the N, when you're trying to move here, it will be having the potential barrier. What is the potential barrier about? This potential barrier is not to let too many electrons falling from here to there. Okay, this potential barrier, we also denote it as a VBI, which is a potential energy. Remember, whenever there's a positive charge and negative charge, there must be a potential energy. And this VBI is trying to maintain the equilibrium between the major electron and major hole concentration, which means that in this VBI is trying to stop too many hole flowing from here to there, or too many electrons flowing from here to there. So this VBI, the main purpose is to maintain the equilibrium between the majority of the electron and the hole. Okay. So this is the thing. Potential difference across the junction cannot be measured with the voltmeter. Okay, you cannot put the voltmeter here. It's kind of impossible. You cannot do that. Okay, because this will form between these two things. Okay, you cannot measure that. But somehow this potential, it maintains equilibrium and no current is produced. Imagine that in this thing, P and N. Just now when I'm saying that, let's get back to here. So this is let's say P is a negative, positive, N. P and N will be having one V. This thing will be having one V also. This V and this V will be cancel each other. So that's why there's no current flow to over here. Okay, let's try to play around with the formula. Let's see this. According to the graph, let me remove this. Where is the side? Okay. One constant rule is to mention this. VBI will be equals to this Fn and this Fp. Why this Fn and this Fp? This Fn is coming from the gap in between the EFI and EF. EF is always the constant when you are going to across the PN junction. But the EFI can be changed. So this thing, when you're adding this and adding this together, it will become the VBI. Okay? But then we may see the N region first. We deal with this formula. We always play with this. And see exponential EC minus EF over KT. And then we can also rewrite this as the Ni exponential EF minus EFI over KT. If you still remember this, hopefully. Then when we are looking at this, EFI minus EF equals to this thing. EFI minus EF equals to this Fn, negative Fn. Then we just need to replace the E Fn here, KT. And then right now, we are going to set this NO to ND because it's a majority. Last time we played around with this. Then we are trying to move everything here. We will get this KT over E, ln ND over NI. On the other way around, we can also get this. The other side, we do the same thing, but we are using another formula. So we'll get this FP KT E ln NA over NI. VBI will be equals to the FP. You just need to add up these two things together. KT and D over NI squared. And then this thing, we call it as a thermal voltage. This is the way for us to calculate the VBI. So you don't have to remember all the calculation, but you just need to know how to use this formula only. So for example, normally question will ask in this way. Consider a PN junction, silicon, of Na equals to 2 times 10 to the power 17. Then Nd is 10 to the power 15. Calculate the VBI. Okay, one hint is T equals to 300K. Then your VT, KT over E, will be equals to 0.0259. 0.0259 multiplied by ln Na and D divided by Ni squared. In this case, we are going to use 1.5 times 10 to the power of 10 squared. So you just need to multiply in this way, then you can simply get the word in between. Okay, this is the way we do it. Okay, let's try one more example here to see how we're going to calculate the VBI. Okay, this is also silicon, T equals 300K, and A and D calculate the VBI. So the formula will be something like this. Let me write here. VBI equals to VT ln NA and D over NI squared. This thing will be KT over E. In this case, this is a 300K, so we just need to use 0.0259 to settle this. Okay, let's try this. So after you have done, type your answer into the chat box. Okay, got cancelled because our answer already. 0.736. What about the rest of you? Did we get the same answer? Okay, 0.736. Let's wait the rest of you if you can get the same answer. When you think you're so lazy, just type +1. You know you're in the Facebook. Okay. We try one more example. Imagine right now you are going to have a garden as a night, and then your NA is equals to, let's say, 10 multiplied by 10 to the power 20, and D 5. Okay. Also 300K. Then calculate the VBI. Let's see what you get. Also the same, if you have done that, then just type your answer there. Okay. Okay, right now we got two different answers. One is 1.62, another 1.56. Oh, how come there are two different answers? 1.56, 1.62. Okay, let me create a poll, see how many of you get the answer. What do you get? 1.62, 1.56. Others. Let's launch it. See how many of you. Okay, 1.62. 16 watt, 19 watt, 20 watt. Okay, majority of you can get 1.62. For those who get 1.56, I think maybe it's a rounding problem, like if I'm mistaken. Okay, what about the rest? There are still some of you, 23, 25 foot, another 5 guy, 4 or 5 guy. Okay, 25. Okay, so I believe the 1.56 is the correct answer. Okay. Okay, let's proceed. So we proceed from here. So an electric field is created when the depression region when you are having the depression region, okay, of the positive charge and the negative charge. We assume that the space charge region abruptly ends in here. Okay, imagine that this region we call it as a SP. This region we call it as a SN. And here, this point, we put a negative SP because it's in the negative direction. We put middle as the origin. Positive here, negative here. SP is the magnitude, so that's why I put a negative value here. Okay, so the changes will be somewhere around here. Okay, so you can see that this thing, when you multiply the n by the NA, because we are taking the magnitude level, so that's why we put a negative value over here. NA is the concentration of the acceptor. Okay, then ND is the concentration of the donor over here. So let's continue here. Okay, right now, the thing here is a little bit confusing. I try to explain. Okay, the electric field is determined from the Poisson equation, but this is for your knowledge only lah. Actually, you don't have to have everything. The important thing is to see how you're going to implement this. Okay, then we proceed from here. So first thing, we are having this formula. Just for knowledge, you don't have to answer. You don't have to remember, just to see how we're going to use it. So there's one theory. This is the origin formula. Then negative dx and then ds. We will see this one by one. This thing, electric potential, dx, electric field, and then rho s, volume charge density, this thing, permittivity. But what is the electric potential? The electric potential actually is the energy to move a charge against the electric field. We call it as a electric potential. Electric field, you know, volume charge density, what is that? Which means that volume charge density is your NA or ND. Okay. Then permittivity is a constant. So at first we are going to deal with the electric field. Okay. But this electric field is somehow related to the SN and the SP just now. Okay, the one that I mentioned. Right now, we are going to figure out how we're going to calculate the SP and the SN. So let's see. So at first, we are going to play with these two things first. Rho S, mu S, and the negative dx over dx. Negative become positive. Don't worry. So we play with the N region. In the N region, ND, dND, dND will be equal to this one, dx, ds. And then you are going to move this dx over dx. And then try to do the integration. You get a yes. But this one is to do the integration corresponding to the s. Since you don't have an x here, you just need to add an s. S plus a constant. So when you set E as a 0 in Sn, when your S equals to Sn, your E will be equals to 0. Okay, so you put 0 here, then your C will be equals to the Sn. This one, Sn. When you put 0 here, E and D, Sn plus C. Your C will be equal to the negative value of this. So, first part, you get this. US Sm minus S. Okay? So this thing is the electric charge between the 0 and the Sn, which means that, okay, this Sn. So when your value is changing from here to here, S1, S2, S3, S4 until the Sn, you just need to put the value to see what are the electric charge based on this formula. This is the first part. So, wait, what is it? Why is this here? Okay. But you might be wondering what is mu x? This thing. This thing we call it as a permittivity. This permittivity actually is a constant value. Okay. This thing, mu O, you can get from a constant list. Is somewhere around here. Yes, this thing. Okay. 8.85 times 10 to the power 14, negative 14. This one, negative 14, this thing. Then this thing, mu R, depends on the what type of the semiconductor you're using. If you are using the silicon, it have the odd number. If you are using a different value, you are going to have a different number. The further content you can look is based on the previous slide. Okay, remember there's a slide. There are 3 of the object there. So it's about the lecture 5. Okay, this thing. Is it given here? Okay. Dielectric constant, this thing. This thing. Okay, this one is the mu R. 11.7, 13.1, and 1.0. Okay, this is mu R. So you just need to replace the right value to there only. Okay. And then, I think I don't want to explain too many things on this because it was too many derivation. I don't want to waste a lot of time on this. But the most important thing is, eventually, after all the derivation, you'll get these 2 formulas. Okay. One formula is this, Sn. Okay, let me write here. Okay. Sn will be equals to 2 S VBI E and D over NA. Sorry, this is an NA over NB. Then 1 plus NA plus ND square root. Another one is SP. 2 mu S VBI D and D over NA plus ND. Okay, all you need to know is these 2 items only, because just now, after all the derivation there, all this thing, everything, the purpose is to derive these 2 formula only. Okay, so we just need to know how to use it. Okay, so from this thing, you can know that Sn is a SP. The only difference is between this and this only. One is NA over ND, another one is ND over NA. By using this, this one, this is a P, and SP is here, SN is here. W will be equals to the SP plus SN. Okay, this is the purpose we derive all this thing. The purpose is to calculate all the SN and the SP. Or the other way around is you can integrate these two formula together to become one formula. NA plus ND, NA and D square root. Okay, as I mentioned just now, this one is the constant value. If this is a silicon, 11.7 multiplied by the MO, BBI, you can calculate it from NA and D and NI. Then E is a constant, 1.6 times 10 to the power of negative 19. Okay, let's see how we're going to use this formula. So for example, see this. Consider a silicon PN junction with a doping concentration of the Na. Na is 1.6, 1 times 10 to the power 16, and D 1 times 10 to the power 15. You see, this thing is the permittivity, already give you 11.7 epsilon O. Ni is given 1.6 times 10 to the power 10. Calculate the built-in potential difference, space charge, and the electric field. Okay, if you are using this and this VBI and the space charge W. So VBI, you can use the formula just now to calculate it. 0.0259 ln Na and D over Ni squared. This value is the value that we have calculated just now, which is equals to 0.635. Then for the remaining of field, you just need to replace every single value here. This thing, 117 times this value from the constant list, we by 0.635, put this, then put this thing together. Eventually, your final answer is in the cm. Okay? Then the Emacs. One thing you need to know Emacs, how to calculate the Emacs. Okay? Because just now, we are skipping those derivation. But in order for you to calculate the maximum charge energy, you need to use this negative E and D as N US or E and A as P US. Okay, just need to dump in every value and then you can get the answer. Okay, maybe we can try one more example here. So for example, we have this ND equals to the, let's say 1 times 10 to the power of 14 cm cubed. This is silicon, US equals to 11.7 epsilon 0. Then your Na will be equals to 1 times 10 to the power of 13 cm mass cube. Silicon. And then, let's see what else. Ni. Ni equals to 1 times 10 to the power 10 cm mass cube. At first, calculate VBI, calculate SN, calculate SP, and calculate the W. Okay, calculate this four items first, based on the given information here. So one good hint for you is the mu O here, the epsilon O here is equals to 8.85 times 10 to the power of negative 14. Okay, let's try to calculate this and see what will happen. So calculate VBI, SN, SP, and W. So since we are having the open book examination, so the style is more or less like our test. Okay, you were to ask to calculate the P and Q. So basically there are not much derivation, so that's why I skipped the derivation. The important thing is to how are we going to use all the formula, just like in this case. Okay. So at first we calculate the VBI first, then we can only proceed with the SN and the SP. Okay, I heard our Prime Minister already resigned. Breaking news officially. Okay, first thing, what is your VBI first? I think VBI should be easy to calculate. Okay, we got 0.4175. Let's see the rest of you. And your thing, 0.3965. How can you get this? Okay, you need to see the question because in this question I say that the Ni is 1 times 10 to the power of 10. Okay, see the question. We are using this one. Since this one is a given one, that we are using this. Okay, but if I didn't give you this, then you can use the one from the formula. No, not from the formula, from the datasheet. Okay, if VBI is done, you can calculate the SN and SP. Let's see how we're going to calculate Sn and Sp. So the formula of the Sn is 2 epsilon s BBI E NA NT the denominator square root. Okay, try to calculate the Sn and the Sp. 2 mu s BBI D, this is just terbalik, and D over NA, NA plus ND. Okay, left a bit. Okay, this thing. Okay, we got the SN value already. Let's wait for the rest. Okay, so let me write down BBI is equals to 0.4175 with SN 7.0089 times 10 to the power -5 cm. What about your SP? Okay, we got SP value. SP also the same. Seriously? Excuse me. Excuse me. Sorry. So SP is times 10 to the power -4 cm. W is to add these two things together. Okay? Anyone can give me the W value? W is to just to add up these two things only. Okay? So this will be 7.7098. 9 or 89? 9, yeah. 4 cm. Okay? So this is how we deal with it. So you might be wondering, what about the uh, Emacs? If we are requested to find the Emacs, all we need to do is to, using this formula only, negative E and D Sn over epsilon S. You might be wondering, what is the negative value here? This negative is representing the direction only. Okay, so you just need to replace every value here, and D you already know that. Sn you have calculated it. This thing you also know that. Then calculate me the E maximum. Okay, you can start doing now. Okay, what's your Emacs? What do you get? Okay. So you get 1.083 times 10 to the power 3. The rest of you, do you get the same answer? Which is there's a negative value here, represent the direction only. So after you get your value, just type over here. Okay. Most of you can get the answer, I believe. Okay, let's see if there's any other different answer. Okay, let's try another example. So imagine if we have removed this. So right now, this one is the germanium. And then your Na is also 300K. Germanium is, let's say, Nd. Then 10 times to the power 20. Na 10 to the power 10. CMS cube. CMS cube. And I get from the slide, the table that I showed you just now. Mu R get from the slide. These two get from the slide. What else info do we need? Okay, let's see. And this one we have, this one we have, this one we have. Then your mu S will be equals to this. Okay, so at first, try to find the VBI, SN, SP, W, and also the Emacs. Let's take the magnitude value of the Emacs. Okay. Okay, you can start now. Then you all calculate everything first, then only see the answer. Okay, with me for a while. Okay, we got an answer already. So let's see. Sn equals to 8492 times 10 to the power maybe 12. SP equals to 0.0185. W 0.0185. What about your Emacs? Okay, we get an answer. 11. Emacs, we need the magnetic value, so just get it to positive. Okay, Junction, for your Emacs, do you get the same answer? Okay. Guessing, for this three value, do you get the same answer? Okay, what about the rest of you? Yong Jie, Ong Mei Ling, what answer do you get? Okay. Same. So, what can you notice from here? You can see that your SP actually is much bigger than the SN. Why is that happening? Because your ND is more than the NA. Okay? So in this case, when you are seeing SN is more than the SP or SP is more than the SN. So if you plot this thing out, okay. So for example, this. So your SP is 0.085, then your SN is very, very small, which means that this is very small, somewhere out here, and this is very big. Okay? Because your NA here, ND here, so this will all coming here. Okay. In this case, we will call it as a one-sided junction. If one is bigger than another one, much bigger. Okay, from here you can see that. Okay, so okay. After this, now we talk about all the forward bias. Everything are in the forward bias. But what happened? Sorry, just now the one is in the, let's say, a zero bias. What happened if we connect this thing into the reverse bias? So imagine if we are converting this thing into a reverse bias, we are actually providing another voltage energy here. We call it as a reverse voltage energy. And this thing, if we want to calculate the SN, SP, or W, everything there, we need to consider this VR factor, okay, which is the voltage, reverse voltage. But how are we going to do so? So for example, this thing. If you are providing a VR here, originally you can see your EF is still the same. But since VR is provided here, you can see there's a gap in between. But what about the formula wise? Your V total total barrier will become VBI plus R. Okay. Originally, you are calculating the VBI. Yes. VBI equals to, let's say, 0.0259 ln and A and D O and I squared. But after introducing VR, you need to use VR plus VBI to become the total barrier. So for the remaining, for example, the width, you also need to consider this. For example, your SN. Okay. Okay. This VBI, you also need to add VR. VBI plus VR. VBI also need to add VR. Okay. Then your Emacs, you also need to consider this VBI and VR. So for example, let's see this. Consider a silicon PN junction with a doping concentration of Na 1016 and D 1015. And then your mu S will be equals to 11.7 UO. And I still the same. We use a 1, not 1.5. 1 times 10 to the power 10. So assume the VR is given there. So let's see. We calculate the SN and SP. SN and SP, we can use back the same formula, just that we need to add another VR inside there only. So for example, this is a SN and SP. SN 2 US VBI plus VR over E and AOND 1 NA plus ND. Okay? Square root. NP also 2 US VBI plus VR over E and D over NA NA plus ND square root. And then first you need to calculate the VBI first, equals to 0.0259 ln NA and D over NI square. Okay, let's go back to the question just now. Okay, here. So by using this three formula, we calculate the VBI, SN, and SP first, based on all the information here. So after you have done, you type your SN, SP, and the VBI. Okay, what do you get for this VBI? Anyone? Or maybe what do you get for the VBI? VBI 0.6560. Then your SN and SP. Okay. 8.7744 times 10 to the power of maybe 5 SP. 8.7744 times 10 to the power of negative 6 cm. You guys get the same thing? The remaining of you? Wong Ka-sing, what do you get? Okay, we get a different answer from Wong Ka-sing. 1.0847. What about your SP? Okay. So which one is the correct one? Ong Mei Ling or Wong Ka-sing? So let's vote to see who will be the winner. Who is the winner? Ong Mei Ling, Wong Ka-sing. Count it. Same with TA. Okay. We have the third answer. Same with TA. Okay, maybe I delete this word. Who will be the winner? Wong Ka-sing and then Ong Mei Ling and Yong TA. Let's see. Siapa menang? Okay. Yong TA 7 vote. 10, 12, 15. What about Ong Mei Ling and Wong Ka-sing? At least you vote for yourself now, right? Seriously? You give me your answer, but you don't support yourself. Okay. Okay, I guess Ong Mei Ling vote herself, sorry. Okay, most of you can get the Yong Qi's answer, about 20. Okay, even Wong Ka-sing himself also get Qi's answer. Okay, so let's see. But just now we have another formula, which is this one. Where do we get this one? Actually, this one is coming from the, oh sorry, this Emacs is coming from this formula. Okay, when you integrate this Sn and Sp together. So that's how you get this Emacs. Or even the W, this thing also consider these two things already. So let's see. Okay. Imagine. Okay. Sn equals to the 2 mu S VBI plus VR over E and A and D. Then this thing 1 over NA plus ND of SP equals to 2 mu S PBI plus VR E ND over NA NA plus ND half. Okay, so W is SM plus SP. So we take this as A. We imagine this is a A, this is a B. This will become the A and A over ND E half plus A and D over NA get multiplied by B half. Okay, and then let's see. So this is the W square root A and AB over ND plus square root. Then this was a and D and A over B. Okay, and then let's see how we're going to do this. If we square this, so if we square this, then we will square this thing together. Okay, then this will be the A and AB and D plus A and D and A B, and then plus a 2 square root A and AB and D square root A and DB and A. Okay, and then this one's A, B, sorry. So we do this first. Okay, this thing multiplied by an A and A and D and D. Okay, then this one will be the AB and A and D and A square plus and D square. And then don't left out this thing. 2. So you have a square root, and A is here, B is here, and you also got one thing is a square root and square root and then D, square root and D and A, then this to be all deleted. Okay? So this thing is a remove. Okay, then you try to square this 2AB plus AB. Then you have to do this. AB is D and A square plus ND square. So it should be outside. Then plus 2AB. Okay, let's see how does the formula look like. Okay, we almost got there. Wait. And then AB and AB. Square root. Okay, what is AB first? A is this. Okay, we multiply this thing out. You will get NA square plus ND square divided by NA and D. Then you have another 2. Okay? So I think 2 somewhere here is something wrong about here. This 2 shouldn't be there if I'm mistaken. Okay? So your AB, your A is 2 mu S VBI plus VR over E. Then your B is 1 over NA and D. Plus ND. Then your NA square plus ND square NA and D. Okay? So you have a plus 2. So eventually, I believe if you continue to simplify here, you will get this thing. Okay? Final answer should be come out with this. But maybe there are some miscalculation that I have done just now. So you just ignore that. The important thing is how we're going to get this. NA plus ND, NA and D. Okay? Square it. So this will become W. So there are 2 ways to calculate the W. The first is to calculate the Sn plus Sp, get W. But if your question never asks you to calculate the Sn and Sp, you can straight away use this formula, this one, to get your W. Both will give you the same answer. Okay, so any questions so far? Okay, if no question, maybe we stop here for today. I will see you by this Friday for the lecture class and the tutorial class also. Okay, so 3 p.m. there will be the announcement from our Prime Minister again. So I guess this thing will be his resignation. So if you're interested, you can go have a look and see who will be our Prime Minister again. Okay, so I think that's all for today. Thank you very much and have a nice day. Okay, bye everyone.